Başlayalım mı?
Başlamadan daha gelmedi. Biri gelmeden sonra Selim diye birisi Selim kim?
Second day of the 6G conference. Today we will continue with the keynote speech and conclude our conference with a lunch, dinner and tour of the Bosporus. We hope to see you aboard. Now, to introduce our first keynote to the day, I invite our keynote moderator Halise Türkmen.
Welcome all. Our first keynote speaker is Dr. Ali Taha Koç. Dr. Ali is the president of the Digital Transformation Office. After his graduate studies, he joined Intel as an R&D engineer. During his time, he has developed numerous R&D engineer at Intel. During his time, he has developed numerous patents and publications. Returning to Turkey in 2014, he worked as a chief counselor of the Prime Ministry and head of information technologies of the presidency. Dr. Ali also managed the formation of the State Information Coordination Center and is a board member of TürkSat. Today, Dr. Ali will discuss the impact of next-generation wireless communication on Turkey's digital transformation. Welcome, Dr. Ali, hoş geldiniz.
Hello. I'm not seeing the screen, but hopefully everything is going to be okay. So the starting point is I'm just trying to use all my patents and then have a word list. So, and then it forms my name. So that's my, all of the patents that I have. So dear guests and the participants, first of all, I would like to thank everyone who contributed to the organization of this conference. I'm so happy to be here. As a Bilkent grad and after the United States and then lots of work at Intel, I came back to Turkey, and then I started working as a government officer. But before joining as a government officer, I worked for Intel, so I love to use some of the Intel slide sets, so it is kind of a old-fashioned. But one of the things that I want to talk about today is just that phrase that I love about Intel. Intel used this phrase a lot. Intel, the evolution of a wireless revolution. But the good thing about this phrase is very key because when you change one word, it fits everywhere. The evolution of internet revolution, evolution of agricultural revolution. But nowadays in Turkey, it fits very well for the defense industry. So nowadays in Turkey, we are building the best and the greatest UAVs around the world. So we can call it the evolution of Turkey's UAV revolution. So what happens in the UAV domain is with the young, talented engineers and with the Bayraktar's family's leadership, currently we are building the best and the greatest UAVs of the world. So this is a good example for us, and then if we can do it once, we can do it again and again. So right now, our job is to do the same successes or same achievements in the wireless domain. Today we are here to show that if we can do it in the defense industry, which is very competitive, which is very hard to enter the market, why not? We can do it in the wireless domain as well. Hopefully, everybody knows that we missed the train in 4G. We have a product, but definitely we are not that competitive. 5G, hopefully we're going to make it better and better. We're going to be more competitive, but we need to be pioneer in the 6G world. So, but we need to do something, not all of the things. So that's like another problem that we have. We need to do a thing which is going to be unique for us, and it's going to be, right, like the UAVs that we do. And hopefully we're going to do the same thing in the 6G world. Another thing that I wanted to talk about this slide set is competition is coming very harsh. They are not standing still. So in Intel, we always work with 802, IEEE 802 domain as well. Compared to from Wi-Fi 4 to Wi-Fi 5, Wi-Fi 6, and Wi-Fi 7, and think about it, Wi-Fi 7 is gonna broad at least 5 gigabit per second speeds. So 6G, the researcher that we need to focus a little bit more about the disruptive technologies if you want to compete with Wi-Fi domain as well. So that's the reason that we need to be careful about what we are gonna do. So since the first generation, as all of us know, that the telecommunication technologies have been rapidly evolving. Performance criteria such as capacity, speed, latency, energy efficiency, and reliability are constantly improving in each generation. As all of us know, in first generation, we only have the voice communication, and 5G, with 5G, especially starting with the 4G though, but with 5G, we have massively things are communicating to each other, massive machine type communication. And guess what happened? With 5G, we'll transform every human being into a data production factory. So instead of being a human being, we're going to be standing still, and with all the IoT devices that we have, we're going to act as a factory, and the output is going to be data. So that's the reason that the 5G will transform every human into a data production factory. We are all excited about these extraordinary developments in wireless communication technologies. As of today, the worldwide launch of the 5G is not yet completed, but it's coming. In fact, many countries, including Turkey, we are still using 4G mobile networks. And in here also we have the LTE 4G networks, 4.5Gs. However, we have moved beyond 5G, and today we are talking about 6G. Last year we also talked. Last 2 years we have been talking about 6G. So it is time for us to act faster, because we are already exploring the potential innovations that 6G can bring to our lives. At the same time, our country is trying to establish its own 5G ecosystem, because without an ecosystem we cannot be successful. We don't need any lone stars. We need an ecosystem. So ULAC Communication continues to work on developing some domestic and national solutions for 5G. We also led the installation and use of the 4G ULAC base stations across all presidential compounds. So that's a big achievement for us. Why? It is presidential compound. It's not a test-based. It's not a rural area. It is the niche area where president works. So we just swap all the equipment from the well-known equipments to ULAC. Why? Because our president trusts in the domestic and national product. So we moved all our product to ULAC. Whenever you come to Ankara, any of our presidential compound, the coverage is going to be provided by ULAC base stations. So that's a key achievement for us, and also it has too much meaning on it. Because why? Our presidents believe in, even in the wireless technologies, the national and domestic products. Also, last month we have launched Turkey's 5G journey at Istanbul Airport. There's also another meaning over there, because as you may know that we have a vision that Istanbul Airport is going to be a hub or transit location for all of the journey of the people all around the world. So we started our journey of the 5G over there as well. But even I went as a protocol and then I just sit there, I'm in my roots, I'm still an engineer. I pick up a spectrum analyzer with me to airport. And that spectrum analyzer also a domestic product. Aselsan built for me a Meerkat device. So when I went to this 5G launch, instead of listening to talks, I just do a spectrum analyzer and then look at that if there's a real 5G network over there or not. Yes, we have the 5G network over there. And I did some speed tests and I got 1.5 gigabit per second speeds. To say the truth, I don't know how I'm gonna use 1.5 gig of speed, but at the end of the day, I saw the speed, I'm so happy. So if you have any time travel through the Istanbul airport, we have the 5G available there. We are expecting, but the 6G is going to enter into our lives around 2030. Researchers and engineers are already focused on the 6G standards. So today we're going to talk about the standards as well. When I was working at Intel, I always attended the standards, and I know that the importance of how to manage your ideas and how to support your ideas in the standards. So if you don't go to the standards, if you don't put your ideas or patents in the standards, it's going to be only a research activity. So you need to be careful about what you're doing in the 6G, and then you need to definitely follow all the standards. So telecommunications companies are already shaping their vision for 6G plans, and with 6G, billions of IoT devices will be able to perform complex tasks. With 6G, actually, smart cities, autonomous vehicles, or remote health will be a real story. Currently, with 5G networks, we are trying to do some tests, but actually, with 6G, it's going to be doable and reliable and a real story. But to say the truth, that we have to do everything a little bit faster. Why? If you look at the time from initial development to commercialization of any new generation technologies, it is getting shorter and shorter. For example, for 3G, when it started development, it took around 15 years before it is rolled out. And after that, if you go to 4G, this period lasted around 12 years, and it only takes 8 years for 5G to go through a similar process. So from the research or from thinking of the technologies to having a product or rollout of this technology is shrinking. So we need to act faster. Last 2 years we are talking, so maybe we have a couple of more years, but after that, if you miss this train as well, we are going to have another meeting a couple of years later, then talking again, maybe 7G. But today, this is the time for us. We need to get faster and faster. 6G will definitely transform how we work and how we live. And 6G will bring integration of a new concept, physical spaces and digital spaces. 6G will combine them, integrate them, physical spaces and digital spaces. With this integration, the concept of Internet of Senses will enter into our lives. Internet of Senses not only, currently we are only using the sight and hearing senses, but experiences such as touch, taste, and also maybe smell become part of the digital communication. In other words, we can say that the human brain will become an interface for digital spaces. Maybe in about a decade, maybe shorter, we may be able to participate in online meetings using a pair of 6G retinal implants. This can be possible. With transfer of senses like touch and taste or smell, we can sense upcoming weather events with a small wearable devices, or we can enjoy the taste of a traditional food when we are far away in an online gathering. And also, the good thing about the Internet of Senses, according to a survey, 77% of the participants or respondents believe that Internet of Senses will be useful. So we are good to go. In the 6G, when we have the Internet of Senses, a new technology, disruptive technology, maybe we can compete better with the Wi-Fi and Wi-Fi 7 or the IEEE 802 domain. In fact, many people already experienced such technologies. First experiences mostly with metaverse technologies are virtual reality meetings. But it is just for now. Maybe in the future we're going to have better experiences. With the current 5G technology, such applications have already started to be used, but again to a limited extent. But the challenges of today also applies for the 6G. Considering these challenges, you see that two challenges are so important. The first one is the security, and the second concern is the privacy. Security and the privacy concerns are at the top of the list. As a simple example, during a stressful period in your work life, probably you wouldn't want your boss to digitally sense that you are considering resignation. So you don't want to transfer your feelings. You don't want to transfer your senses. So with Internet of Senses, reality will merge with virtual reality to form a mixed reality. In this case, our brain must adapt to the transition between real environment and virtual environment. During this transition, most probably our brains will suffer a loss of reality. When moving from virtual to physical, the performance expectations will be high as well. Our minds will demand the same speed and capacity from physical life as it is in the digital space. For example, you just want to move from the New York Times Square to Istanbul in a quickly, but your body or physical world is not going to allow it. This scenario can cause some struggle in everybody's life. I just want to give an example about the Indian proverb. I don't know if you know that, but you know, some Indians are riding their horses, and after some point they stop. And the leader of the team leader stop and say that, we travel too fast. Our bodies are here, but our souls are left behind. We are waiting for them to catch up with us. So most probably with the digital integration of the physical and digital world, our bodies are going to be here, but our digital twins or the digital equivalents are going to be so far away. So maybe we need to wait for them. Many things we used to do in physical environment already started to move into the digital space. As the real and the virtual become more blended, we are going to hear more and more often the digital twin concept. So everybody is going to have their digital twins other in any other platform. But this is going to be doable and viable with only with 6G. By 2026, according to some research, 25% of the whole population of the world are most probably is going to use 1 hour of their daily life, 1 hour of daily in metaverse environment. Out of 24 hours, 1 hour is too much. But we are going to spend, currently in Turkey, we are spend around 8 hours in internet domain, and out of 4 hours are social media. I think 1 hour is not much. But with all these wearable devices, hopefully we are going to do more useful things in the metaverse domain. We will watch concerts and matches from our metaverse virtual stadiums. Buying virtual properties, I hope you are not getting into that business, buying virtual properties, but buying virtual properties on metaverse already become a popular investment. But to say the truth that it remains a mystery still how virtual properties will be priced in the future. I don't know how you price it or how much you pay for it, but as an advice, please don't get into that business yet. It is not profitable yet, actually. With 6G, the metaverse will integrate many real-life concepts. As applications like this become widespread, we will need faster and higher performance infrastructure, namely 6G infrastructure. So if you compare with this 6G and 5G, 5G is going to give us around 20 gigabit per second, which is too much. It's all theoretical limits. And hopefully in 6G, we're talking about 1 terabit per second speeds. Capacity is around 5G is 1 million users per square meter. 6G is going to have 10 times higher connection density. Again, bandwidth, as all of us know, Claude Shannon already told us that the bandwidth is linear with the capacity. So with bandwidth around 100 megahertz in the 5G, we are talking about higher band, so we can go to up to bandwidth of 1 gigahertz bandwidths. Latency 1 millisecond, which it's also a theoretical limits in 5G. We are talking about 0.1 millisecond latency numbers. But the most important thing is energy efficiency. Definitely energy efficiency is a key factor for 6G. And also, I'm bored of carrying all my charging devices. So in the future, hopefully we are going to see a device charged by radio signals. So because I'm fed up of having all this connection, and also lately we are discussing with the European Union the unification of these chargers, because all the plugs are different, and you need to carry mobile devices, and next to mobile devices you need to carry lots of charging devices and cables. So hopefully with the 6G we are going to have a device which can be charged with radio signals. And actually reliability is the most important thing. Currently we talk about remote surgeries, smart transportation, but poor service quality is unacceptable for both remote surgery and smart transportation. So overall, if you want to have this kind of technologies, we need to definitely improve the reliability. In 6G also there's another thing is going to pop up, so we're going to lose less human being for the network monitoring and network planning. Instead of that, we are going to use AI, artificial intelligence, for network planning and monitoring. Coverage areas will be managed by AI systems, and all these features have the potential to unlock transformations in many vertical sectors. Perhaps we will witness the transformation of science fiction into scientific fact. Another field where drastic changes will occur is the non-terrestrial networks. When we talk about coverage area, we always mean terrestrial areas and also the antenna towers, big towers, and then skyscrapers. But now, we also need internet access under the sea, over the sky, and in space. As the number of drones and UAVs increases, coverage over the sky has gained more importance. So even currently, lots of the UAVs and drones are flying over us. So currently, studies are conducted that which combines the mobile communication with the satellite communication, and then with combination of the mobile mobile communication and the satellite communication, we can tackle these problems. According to the report on emerging technologies 2021, which is written by the World Economic Forum (WEF), space-based communication network is among the top 10 emerging technologies. So we need to stop looking at the ground and we need to look up. Don't confuse with that movie, Look Up, but we need to definitely, if you want to do some research, we need to definitely look up because satellites are there and satellites market is getting bigger and bigger. And it is estimated that the space economy will grow 74% by 2030. And the value of the market value is going to be around $642 billion. It's too much money. And currently, everybody is talking about this new space race. Now, lately, like 10 to 20 years, there was an internet race, but currently, there is a new space race seems to have been ignited, in which the center is low Earth orbit. So in Turksat, we have all the geostationary orbits or the satellites, which are 35,000 kilometers far away, but we are talking about the satellites which are 500 kilometers far away, which are called low Earth orbit. This race called maybe new space, or someone is calling it, using the same jargon, space 4.0, like industry 4.0, they're calling it space 4.0. Space is used for communication purposes in this space 4.0 or new space, rather than broadcasting or navigation or observation. By launching low-orbit communication satellites into space, many governments and private companies are trying to integrate these satellites with their base stations. These are all Starlink satellites. They look good. When they launch 40 or 50 of them together. They're all packed, and they have one side they have their solar panels, and they open it up. Maybe with your bare eyes, you can even see them when they first launch, because it takes some time for them to separated between each other, so they are planning to have all the internet access all around the world. So the number of satellite constellations will cover the globe and enables the uninterrupted delivery of high-speed internet and communication services. So according to plans or according to projections, the number of satellites scheduled for launch worldwide by 2030 is planning to exceed 100,000. 100,000 satellites around the globe. So in Turksat, we have currently 5 satellites, and we are so happy. Thinking about it, hopefully we are going to have Turksat 6A, and it's going to be our 6th satellite. And then we are talking about 100,000 of satellites, low-orbit satellites. So by SpaceX, Starnet, OneWeb, Amazon, Telesat, a total of 66,000 low-orbit satellites are projected to be in the space. So this 100,000 number is most probably going to be real. So think about it. Right? Everywhere in the terrestrial network, we are covered with base stations. But currently, everything is going to be up with 100,000 of satellites. This will enable conventional smartphones to communicate directly with 5G base stations on low orbit satellites without any additional hardware. This is going to change drastically our way of doing things. So currently, the reliability or communication performance is going to be increased drastically with using the satellite communications. I just want to talk a little bit about the blue orchid tree. I don't know how many of you know the blue orchid tree. I love antennas. I'm a wireless guy, and I love antennas. This is a big antenna. This is the largest commercial antenna ever deployed in low Earth orbit. It is 693 square feet. 693 square feet. We are in Turkey, we don't know what the feet is, so let's move it to the meter. It is 64 meters square. It is 8 by 8 meters. It's a huge antenna array. It is in the space. So it is the beauty. Look at this beauty. When I see it, I believe I fell in love. This is 64 meters square antenna array at the space. It is 500 kilometers far away, but it can directly have the communication to your cell phone. Because why? Because why? Because the capacity, because the trend is going there. Without these big antennas, you cannot have the same link budget and you cannot have the same capacity. So with this, all these antenna arrays, you can do all the researchers can do all the crazy stuff. You can do allomotives, you can do spatial multiplexing, you can do multi-user MIMO, you can do all the diversities because you have the area. So can you put a 64 square meter antenna in top of any place in the terrestrial domain? Of course not. But in the space is empty. And guess what? We have hundreds of thousands of platforms available there. So if you want to do any research, we need to definitely go to the space. So overall, this Blue Walker 3 is a very nice project. And once this satellite up and running, tests will be conducted with mobile network operators by connecting directly from satellite to the phone. The new, actually, not only this Blue Walker 3 is using the satellite communication, the new smartphones introduced by Huawei also have their own short text messaging application, and which is connected to Baidu, their global satellite navigation network. And even in new iPhone models offer a direct satellite communication. So for the terrestrial operators, for all the operators, something is merging, something is coming. I don't know, I don't want to say winter is coming, but something is coming, definitely. So you need to change your mindset because everything is going to satellites. So if you keep on talking about the coverage area using the terrestrial networks, you're going to be out of picture. So you need to think about ahead and you need to look up. So to be honest, this feature excited me the most, the direct satellite connection. We are in an era where satellite connection reaches our regular phones. Concepts such as, but this is a starting point. Hopefully in the future we are going to we are going to hear concepts such as space data center or space mobile networks. So think about it. We have terrestrial data centers. Instead of using our data centers over the ground, what if we move all of our data centers to the space? It's going to be a big change, especially if you have all these laser links and if you have a spatial space mobile networks. Instead of using the fiber optic cables underneath the oceans, maybe we can use the direct communication using the space. And we can have a space mobile networks over there as well. So these are the new concepts it's going to lead up, and then we have to do some research about it. Actually, all of this is going to have an exponential increase in the volume of data generated and transmitted by human beings. So again, at the beginning I told you, right, we are going to be transformed into a data production factory. So all this connectivity and connections, we are going to increase more and more data. So data of this size can only be processed with big data technologies and analyzed with artificial intelligence. So if you want to do any research in 6G as well, you need to be aware of the big data analysis and as well as the artificial intelligence. And it's not hard to predict that with 6G, the use of artificial intelligence will become much, much, much more important. And also, if we go back to the adventure of artificial intelligence, it becomes with a very simple question. Can machines think? Has reached a point where machines can analyze the chemicals in human breed and they can diagnose possible diseases. So now, instead of they can think, they are also smell. So I guess all that's left for AI is gaining consciousness. I'm pretty sure that there's a big question about the AI, whether it's going to gain consciousness or not, but I hope not. But overall, that's another big question, because all the other things that with the AI, you can do it right now. There are also some limitations to this technology. So I just want to go through some of the limitations, but still the AI technologies are getting faster and getting more smarter, but there is some limitations. Let's take a look at our video and then I'm going to talk about it as well. So in this video, I just always give this example because when cars first introduced, people called them horseless carriage because horses simply had vanished in front of the carriage. We moved from the horse-drawn carriages onto horseless carriages. Now we are talking about self-driving cars. But it seems that these AI-powered vehicles are not yet able to recognize horse-drawn carriages. Look at this video. A smart AI car just driving behind the carriage, and it thinks it's a truck. No, it's not a truck. Oh, it's coming back. It's not a truck. Oh, it's people walking. So that's the biggest problem with AI. What happened? So there's an existential problem over here. So this AI system couldn't understand the basic stuff, which is a horse and a carriage. Why? Because it's in data set or the data bank. It never ever been trained with a horseless carriage. But what if with this AI system, if you erase all the knowledge about the human beings, what is going to happen? When you are crossing the road, this AI system is not going to recognize a human being, and what's going to happen? So isn't it scary? So we need to be careful about because of that we are talking about, when we talk about the AI systems, we need to talk about the trustworthy AI. We need to trust this system. It is so powerful, it's so strong, but it depends on the data that it's trained with. So that's the reason that we need to have this kind of technologies in an environment, and we need to test very deeply and truly. As you can see, it is clear that AI has lots of limitations, so we need to be sure that in order to solve these problems and the limitations, we need lots of engineers as well, and lots of research. Thanks to all rapidly developing technologies, the time we spend in the digital world is increasing drastically. So we are talking about more and more in the digital world. Innovative technologies are transforming the way we think, we drive, we go to home, we behave, we do businesses. And information and communication technologies are at the catalyst of this transformation. So we are in the right position right now. If you do any research in information and communication technologies, we are good to go. And this is more and more evident in the statistics of our country. Let me talk about a little bit about the Turkey. The length of the fiber optic cable has reached 478,000 kilometers. But the good thing is about the fiber subscriber hits the 5 million number. And monthly average internet usage per person is around 12 gigabytes mobile broadband, and for the fixed it's around more than 200 gigabytes. We are using more data. And our population is around 84.6 million, but the number of mobile subscribers are around, more than population, around 89.4 million. And if you compare between the 2020 and 2022, internet usage is increased from 79% to 85%. And especially if you look at the age between the 15 and 24, the usage increased from 93% to 97%. So in 2022, 97% of the population whose age is between 15 and 24 can have the internet access, and they're using the technology. So this is our biggest strength as Turkey. This is our biggest strength. So we need to utilize this strength. We have also one of the best e-government systems in the world with more than 60 million users. E-government adoption rate reached to 91%. If you go out, and 9 out of 10 people in Turkey right now is using e-government system. And 15% of the population are between 15 and 24. With this young population, we have great potential in using these digital technologies. So when we're all academics and we know that skilling or training a talent is hard, but reskilling is harder. So that's the reason that these young people, they are still fresh. So we can come up with very good talents, and we can train them with the new technologies. For us, for example, for the digitalization, we are facing lots of problems with the e-government as well. If your age is above 50 and above, it is kind of hard for you to get used to that kind of technologies. But in Turkey, we have 15% of our population is between age of 15 and 24, and they have fresh minds. So right now we have to train them, and we're gonna train them well. So next generation communication technologies will provide the infrastructure that will make this possible. With the 6G, hopefully they're gonna be a little bit better connected, and they're gonna have better technology. In the future, those who produce innovative technologies for artificial intelligence, quantum computing, blockchain, cloud computing, will be superior to those who only use these technologies. So to say the truth, that to sum it up, the only way to predict the future is to create it. So with this mentality, with this vision, what we brought is there are many hidden talents among our youth who are candidates to become Mimar Sinan, Bruni, Ali Kuşçu, Ibn Sina, Cezeri, Cahit Arf, or Aziz Sancar of this era. We call them Technofest generation. We believe that the Technofest generation will be the key that unlocks the door to the future. And we are working hard to raise them with this vision. I believe that 6G conference will be very useful for all of us, and once again, I would like to thank all of you who are already working to shape the world of the future. Thank you again.
Thank you, Dr. Ali Taha. We can take questions now.
Tamam, atış serbest diyelim Türkçesi. Evet.
Hello everyone, thank you Ali. I'm Kamar Abbasi from University of Glasgow. Very interesting talk. You talk about space, that there will be millions of satellites in some time. So isn't it scary that there will be an issue in space debris? So we're going to pollute the space as well, like we polluted our ground environment. Yeah. So will you comment on that, how catastrophic it will be, the space debris?
So you're right. So the space is big, but it's not that big. So if you put hundreds of maybe millions of satellites, definitely there's going to be a huge debris, and then these devices are not going to be fixed, because you know that if you send something to space, it stays there. If it's broken, you'll let them die, or you let them get into the atmosphere and burn. So that's the biggest problem. There are lots of research going on that perspective, but currently the previous problem is most of the time we are talking about the geostationary, right? They are 35,000 kilometers far away, and the debris over there is not that crucial for the human being, but these debris are a little bit closer, like 500 kilometers far away. But again, if they come into the atmosphere, they're going to burn. But the biggest problem is that not for the human being, but for the stability of the system. If they become a debris, they can hit the other working satellites. And then that's the biggest problem right now, how to manage. For example, in terrestrial networks or in flying, you know, we have air traffic controllers. So you need to definitely have lots of air traffic or the space controllers to control the systems. And also there's supposed to be lots of research going on about the debris collection satellites. So some of the debris or some of the unoperational satellites needs to be picked by using some other technologies with the other satellites, and they're going to collect all the debris, and they're going to come to the atmosphere and burn together. So there are lots of research going on that, but that's also a nice topic, maybe not in near future, but in far future, it's going to be a biggest problem.
Thank you very much. I am Başak Özbakış from Vestel. Thank you very much for this presentation, Dr. Koç. What do you mean with these digital twins? Could you please give some detailed explanations or some examples?
So anything that can be a digital twin. So whatever. So for example, in my office, I have my digital twin. You know, this digital twin is trying to model what's my lifestyle, and also anything can be a digital twin in the digital world. For example, most of the cases we are using this for the preemptive maintenance, but we just try to, in our office, we try to map it into real life. For example, my digital twin always, whenever I come to work, also it starts working, and whenever I go back to home, it stops working. But digital twin is the replica of what you are in the real world in a digital environment. Most of the cases, for example, airline companies are using digital twins to mimic the engine performance, and then before flying to any long flights, they are just having the similar technology in their software, and they're trying to have the preventive maintenance so that if there's something is broken, the overall reliability of the engines on the planes are going to be satisfied. But overall, digital twin, whatever we have in the real world, it's going to be in the replica in the digital world.
Okay, thank you.
You have questions, Salah?
Okay, so I'm Sohaib Soleja from Medipol University. I have one comment and a couple of questions. So the first comment is, actually I was hoping to hear more about specifically Turkey's digital transformation, which in my opinion you didn't cover in that much detail. And moving on to the question, so you mentioned about the deployment of 5G at Istanbul airport. That being said, as far as I know, there's no allocation of 5G bands or these kind of things yet. So what is the strategy in that regard? One, because we have to keep in consideration the fact that Turkey is one of the places where the revenue per user is not that high. So in that case, if the spectrum allocation or spectrum is very expensive for the operators, how would you actually motivate them to deploy next generation systems? And along the same lines, so what is the strategy for 6G, let's say, and what is Turkey in general and your specific or your office in particular going to do differently as compared to 5G?
All right. So first of all, in Istanbul Airport, it's a test network. It is not, we didn't launch we didn't auction the frequencies yet. So it's a test network. We just give the same band for all these 3 operators. It is just a test band, but it is live. So if you turn on your 5G phone, it receives the signals and it's operational. But again, it is for testing purposes. It is currently without any auction or without any money. The operators didn't pay any money out of this frequency. But it's a local band, local area, so it's just works inside the airport. The second thing about how we are going to do the auctions, you're right. So around the world, we are following all the auctions, and then we figure out that if the operators spend too much money for the auctions, they don't have enough money left for the infrastructure and all the deployments of all the hardware. So that's the reason that we are waiting for our domestic products to be viable and real. So hopefully we are going to postpone maybe to 2025. So if you look at the 4G, what we did is, as you may know, the 4G is going to start around 2010, and then we launched our 4G systems at 2016, 6 years later. But as you may know, every 2 years the technologies change, so that's the reason that we have a better release of the 4G technologies. So we call our 4G launch as a 4.5G launch. So hopefully, most probably, we're going to have the similar things in the 5G as well. Instead of having the first 5G releases, we're going to have later releases, maybe late 2020s, closer coming to the 2030s. But again, still the $1 million question is the auction. So we couldn't figure out the best way to do that. Either it's going to be an old-fashioned way to having all those people are paying the money for the frequency, or just revenue sharing models are also discussed. But we will try to find the best way. Maybe there are some also possibilities that we can skip 5G and we can have the whole capacity coverage with the 4G, and after then we're going to have maybe 6G quicker than we have the 5G. All right? So again, the same mentality is going to go away. So we are looking for the domestic products. And then with the Ministry of Transportation and Ministry of Science and Technology and our office, we're going to support all the technology and all the research activities to have the products a little bit faster and then more real. So currently, as you may know, that we started couple of years back, like 10, 15 years back. We have, and also we have a couple of other companies, but we need to have a bigger ecosystem. So we are trying to build up this ecosystem, and with this ecosystem, hopefully we are going to have our 6G platforms ready before we have our auctions. Thank you.
Our time is almost up. We can take one more question. Mohammed.
Very nice presentation. I like the new style always. So I like your point about space data center, because I think that's fundamentally needed if we really wanted to get good performance from the space communication, because we all know the edge computing. So if you want to get the edge to be close to the space station, then you have to fly it up. So that's I agree with you, and it's really a good point. So my question to you is, actually there are two questions. The first one is, the 5G airport is really great, but what do you think about how to repeat this? Because we all know that enterprise transformation and B2B, this is a real deal about 5G or 6G. So your effort in there, I would like to hear it. And also the second one, what's your vision about the digital divide in Turkey? And I know it is not about not using the internet. The real digital divide when the holistic connectivity. So the connectivity is not going to be just the low size. It's, as you mentioned, digital twin. So how do you envision in 5 years or whatever, Turkey, this concept of new digital divide? What do you envision in there? So only two things.
Yeah.
But thank you so much for your presentation.
Thank you again. So what we're planning to do is we're just going to have the same mentality for the 5G test. So we're going to have maybe, we have a domestic car company called Talk. So that factory is going to be also a new 5G factory. And we're going to talking with all these companies to having local compounds, having a private 5G networks, and we're going to slowly test them, and with with the domestic products, because again we missed the train with the 4G, and we don't want to have the same problems. If you get into technology, yeah, we definitely, Turkey somehow missed it. The luck is here, but we couldn't sell enough, actually. Maybe we couldn't sell enough. So what we are planning to do is, if you need to be competitive. We figured out that. So you need to competitive with the performance-wise. Also, you need to competitive with the price-wise, because the operators are always looking for not the performance-wise. And then when if the price is too high, they are always talking about this domestic product or the national pride becomes inside. So they are talking about the old financial reports. So that's the reason that we need to be very careful about how we make these products as well, because the bill of materials and then how we are going to do the licensing fees. We need to think about, currently it is just a learning experience for us for 4G, and 5G is going to be a little bit, we are more aware of what is going to happen if you want to become a big. So currently, if you become big, you know, all these big guys are going to come after you. So that's the reason that we need to be careful about how to become, how we need to learn how to produce. Right now, the next step for us, we need to learn how to become big, like what we did in the defense industries. Right now, everybody's talking about our UAVs, but maybe in the future, everybody's going to talk about our 6G, for example, power amplifiers. With gallium nitride power amplifiers. Maybe instead of doing all the 6G modules, maybe we're going to do a power amplifier which all the operators or all the vendors are going to use. So the strategy is not to build everything, but to build one thing which is going to be unique for you and sell to everybody. So not for the domestic, but for all the other companies as well. So that's our strategy for the holistic approach of this digital twin and the connectivity digital divide is the biggest problem. And lately I was in the European Union discussion about even Europe couldn't solve these problems. How? No one is. That's I think that's going to be $1 million question, right? Whoever solves it is going to get the Nobel Prize, maybe. But again, with how we're going to do it, because it is not profitable to have the whole coverage all around the country like Turkey or the United States. But otherwise, you cannot move everybody into some small location. Then it's become polluted and pollution and everything. So there needs to be a balance, but maybe the balance is going to be with this satellite communication is going to be helpful for all those stuff. But still, to say the truth, I don't have a clear answer to that question. Thank you.
All right. I'd like to thank Dr. Koch Başkanım, for this wonderful speech, for this wonderful keynote. Actually, I invited Dr. Koch for yesterday opening speeches. He said that no, I want to be with the technical guys. I like to listen all the talks, and I'm glad that he did that. Actually, it was very nice to see all these technical discussions, and also good to have him actually in the president office as a decision maker. So, thank you again, Dr. Koch. Our next speaker is a very good friend of mine, Dr. Selim Alini. I don't know, everybody knows him. I don't know whether we need to introduce him. Maybe we can formally, but thank you, Selim, for coming. Halise, do you want to introduce him? Okay, well, maybe formally, but I know that everybody knows him very well.
Welcome, Professor Mohammed Selim Aluni. Professor Mohammed is a distinguished professor of electrical and computer engineering in King Abdulaziz University of Science and Technology. He has a broad research profile with numerous valued contributions to the academia. Throughout his career, he has accumulated many distinguishing awards, including the IEEE Vehicular Technology Society James Evans Avant-Garde Award and Technical Achievement Award of the IEEE Communication Society Communication Theory and Technical Community. Professor Mohammed's current research focuses on providing connectivity to the unconnected in future generations through aerial and space networks. Today he will present the 6G vision. Welcome again.
Thank you. Do you hear me? Yes. Okay. I would like first to thank the organizer and in particular Dr. Hussein Arsalan for inviting me to come here to share with you some of our thoughts and to meet some of the good old friends. So the title was advertised that what 6G should be. And the title here is in a way my answer, which is one aspect of 6G I would like to emphasize and I would like to talk about today, which is this kind of objective that many of us are trying to pursue as part of this 6G activity, which is about connecting more of the unconnected people worldwide. So as you know, we are at a time where basically quite a bit of brainstorming is happening about our vision for 6G, and most of the research is directed towards, of course, trying to push the envelope in terms of going to higher speed, lower latencies, connecting more device per unit coverage area, as we have done in the past when we developed 4G and 5G. But 6G should be about a few other things. Dr. Ali actually mentioned some of the key aspects, in particular energy efficiency, but also another important aspect, which was also touched upon in the previous talk, is about this connectivity divide that we still suffer from. I mean, the numbers vary from kind of some reports to others, but what we can say is roughly 2/3 of the world population are well connected, and about 1/3 are still, let's say, either not connected or underconnected. By underconnected, we mean people that are still living on a 2G type of connection. Basically, they are not fully enjoying the benefits that come with internet. The reasons are too many to kind of go through right now. I would like to focus on one particular reason that will be kind of what I would like to push towards throughout my talk, which is the backhaul problem. It does not make much business sense for mobile network operator to dig hundreds if not thousands of kilometers in order to lay some optical fibers with an objective to reach remote, hard to reach area that tend to be rural, tend to be also low income. So the backhaul is one of the main problems that kind of lead to this connectivity divide that touch particularly rural areas in developing countries, but actually sometimes also in developed countries. So again, there is this kind of interest in trying to, let's say, bridge this digital divide and break this vicious cycle in order to improve the quality of life of many of the people who live in these remote areas. And in a way, COVID-19 showed that the digital divide or the connectivity divide is in a way a modern face of inequality between the have and have not in a digital context. And providing this connectivity in this era is similar to basically providing a highway or a train line connecting a remote province and bringing prosperity to that particular region. But also bringing connectivity to one particular region can actually incentivize people not to move out of the rural areas and move to urban environment. Because at the end of the day, if you are able to work and enjoy a good quality of life while living in suburban or well-connected rural areas, can basically, let's say, lead or trigger a counter-urbanization process, which is one of the other main problems that we are suffering from. All these mega cities that are basically emerging worldwide is a trend that maybe we can reverse by connecting more of these remote areas or suburban and rural areas. So we can move out in a way from this, we can view it as a narrow concept of smart city to something broader, which is smart villages, smart hamlets, smart rural area, or more generally smart living. Now, I mentioned like the backhaul as one of the main challenges. So one other way of looking at it is to look at this basically diagram, where basically we are looking at the quality of experience as function of the cost per user in remote low population density area. So we know very well that optical fiber cable are a great solution in dense environment, but obviously, as I mentioned earlier, it does not make much business sense to try to connect these remote rural areas with cable, because it's a quite expensive solution. Now, classical also satellite solutions that are more kind of designed towards TV broadcasting are good from a cost perspective, but they don't give the nice or the desired two-way high-speed connectivity that internet browsing requires. So what we're after, if you will, is this corner, the upper left corner, which we can call the global connectivity holy grail, which is how we can provide a good quality of service, but at a low cost. And in a way, if we achieve that, we'll be able to fulfill this prophetic, let's say, vision that Nikola Tesla had about 100 years ago. And if you read that statement carefully, you see he was already thinking in a 5G or 6G terms in 1919. So how can you achieve that? So going back to the backhaul problem, actually it is exactly the opposite way we design networks in a dense urban environment. When you go to a dense urban environment, you densify. You put more and more cell to be able to capture more and more traffic. When you go to rural area where you have very low density population, you want to go towards more bigger and bigger cell. So macro cell is the way to go. How can we achieve a bigger coverage in order to capture the few scattered users within your coverage area? Now, how can you achieve this macro cell is by going in altitude. So one very basic way to do it is, for example, to start reusing TV towers. So that's kind of a project that we started, and by the way, we are not the only one doing that. That's an approach that has been kind of, let's say, pushed forward a few years ago. We kind of analyzed it, and recently we are having a paper that is going through the review process that's available on archive that basically explain the benefit of you reusing TV towers to basically provide these tens of kilometers of coverage. You want to go higher, you go, for example, for this tether balloon type of solution. There are a few companies in the US that are basically selling this technology. We are talking about blimps or airships. I don't know how you want to call them. No, they have different names. They are basically flying at roughly between 500 to 800 meter altitude. They are tethered. The tether is there to provide power supply, to provide often also like a backhaul, like a fiber optic. And then you can put an access point or a base station, and you can create like a few tens of kilometer radius macro cell. Okay? So that's one way to gain altitude. You want to go even higher? Then there is this emerging concept of high altitude platforms or high altitude pseudo satellites. We are talking here about platform operating in the stratosphere at an altitude roughly of 20 kilometers. Just for calibration purpose, the airplane we use to travel fly at 10 kilometers. So we are at twice the altitude of regular airplanes. There are a few ongoing projects, the so-called HAPS, come in different forms and colors. They can be in the form of big drones, they can be in the form of balloons, they can be in the form of blimps or airships. So there are projects like Thales, for example, has the Stratobus, which is a blimp. There is Zephyr, which is basically an Airbus type of project. So there are a few interesting projects ongoing right now where basically they believe in this concept of hubs. With the hubs, you may have a coverage of about 200 kilometers. Okay? So we are still in the air. Okay? Now, going now to what Dr. Ali talked about earlier, you can go even higher, and the ultimate solution is to go for satellite. And when we talk about satellite, basically we are talking about the different families of satellite, going from the LEO from 600 to 1200 kilometers, all the way to GEO at 3600 kilometers. So all of these solutions are there to allow you to basically get into height and bring up or increase your coverage area. Now, if you want to put everything together, and that's the key word, that's one of the key basically direction that many of us are pursuing within this kind of 6G brainstorming exercise, is this, and the kind of keyword we are using is integrated ground, air, space network. Some people are using actually now the word beyond integrated with unified. Unified basically ground, air, space. And again, by ground we mean like the standard terrestrial base station that we are all aware of. By space, all the families of low altitude platform like drones, all the way to tether balloon, to basically high altitude platforms or hubs. And that we are still in the air type of space, all the way to all the way to space when we start talking about satellites. But we are talking about an integrated or unified system in the sense that there will be no one size fits all. It will depend on the kind of configuration. It will depend on the type of density population that we are trying to serve. And you may end up having either a combination of these type of layers working together to provide connectivity, or one, among others, depending on situation, trying to provide service. Now, in this context, I would like to kind of highlight, I mean, there are a lot of interesting research direction. Professor Ali talked about, for example, antenna designs. That's a great research activity, beamforming. How can you do beamforming from the sky in order to basically bring the capacity where needed and talking back to a phone? That's one research direction, and maybe some of you are active in that. So one particular area that have been of interest to some of us, and including in my research group, is how to use free space optics. And I know in Turkey there is quite a bit of nice activity in this domain. So I call this part of the talk A Light in Digital Darkness, to emphasize how optical wireless communication or free space optics can help basically in the context of bringing connectivity worldwide. So as you know, spectrum is a scarce resource. There's quite a bit of competition among many applications to get access to spectrum. And when we talk about spectrum, often we think only about the RF spectrum, but the spectrum is much wider than that. And you can start thinking about the optical band as a possible band to use for communication. So in particular, free space optics is a technology that is quite mature. Quite a bit of research that has been done over the few last decades on free space optics. It's kind of basically, I would say, and I think many of you hopefully will agree with me, that there is nothing better than FSO to bring super high speed in a wireless fashion. The same way there is nothing better than a fiber optic to bring super high speed in a wireline connection. But of course, FSO comes with its own challenges, atmospheric losses, pointing issues, weather type of condition. And to make a long story short, it's a technology that struggled to make it in the terrestrial market. For a variety of reasons, maybe we can talk about during the break, but it has its issues because, I mean, in a nutshell, the RF technology is still so strong and the lobby is so strong that it's hard to compete with RF on the terrestrial market. However, I think there is a nice sweet spot for space optic, for aerial and space networks. So the idea we are kind of pursuing, again, with few other kind of researchers, is how we can use free space optics to create backhaul for aerial and space network. And this is not science fiction. There is quite a bit of interesting progress from an experimental side, basically showing why this is really one good approach for free space optics and to solve the backhaul problem for aerial and space network. So here is a vision. This slide is summarizing what I'm talking about. So we are talking about this next generation satellites. Some people tend to call them VHT satellite, very high throughput satellites that can process up to 1 terabit per second. They come typically two-sided. So the first side is the user side. This is the type of antenna that Professor Ali was talking about, where you have multi-beam capabilities. This beam can be moving around. They can have up to 10 gigabit per second type of capacity. They can kind of at some point target like an airship, like a ship or a yacht or a rural area or offloading in an urban environment. So basically these are beams that can be directed where traffic is needed. Now obviously a satellite is acting as relay, so the whole thing has to be basically multiplexed and backhauled. Currently, high throughput satellites are using Ka band as a feeder link or a backhaul link. Now by the 2030s, which is the time where basically these very high throughput satellites are expected to start being in operation, the Ka band is a band that's already under heavy competition. In the sense that part of it, 5G or 6G wants to get hold of that part of the spectrum, and also part of the Ka band want to be transferred to the user link. So basically now these user link are using Ku band. We are running again out of band of spectrum, so some of the Ka band is going to be used for user link. And here where free space optics proposition comes handy, the idea is to use optical feeder link. So this can be for LEO all the way to GEO type of satellites. And this can provide the terabit per second that you need to backhaul basically these satellites. Now obviously, as I mentioned earlier, the optical feeder links come with their own challenges. Pointing is one important aspect. I will talk briefly about it. Turbulence that happens in the first 20 kilometers in the atmosphere. Weather condition, if you have fog, if you have a cloud on the way, that can block your signal, and that's why often these kind of systems are implemented in conjunction with site diversity, which means if you are blocked in a particular optical gateway station, you have to have in your network another optical gateway station can pick up the signal. So that's kind of the vision, where free space optics can fit to provide backhaul to this high-speed network in the air or in the space. So here is in the space. You can replicate the same thing with the hubs. So instead of being basically at 1,200 kilometer altitude or even 36,000 kilometer altitude, you can use the same concept of an optical gateway station, connect to a hubs having a multi-beam type of operations. As I told you earlier, hubs can have a 200 kilometer type of coverage radius. Some of the beam can be used for offloading, some of them can cover some villages, some others can cover some maritime or can provide some maritime communications, but again, it's the same concept. So what are the interesting research that can be done? First of all, trying to assess the performance of these FSO links under some impairment, in particular pointing error as well as atmospheric turbulence, and check how we can mitigate that. So as you know, when you go through a free space optic link, you have turbulence, and turbulence can lead to some what we call beam wander. So beam wandering is like essentially the beam is not going to be stable anymore. It's going to be kind of moving around. And if you go to a lab and see what happens, you'll see basically the beam come dancing. So it's not like fixed anymore. That's the beam wandering effect. The other aspect that you can see is what we call beam spreading, which means the beam opens up, and basically the beam, if you go again into a lab type of a configuration, the image becomes blurred. So these are some of the effects that basically are the result of turbulence. Now, turbulence is modeled as a statistical, we use statistical models to model turbulence. There are quite a lot of channel models. In some of our analysis, we use, for example, the gamma-gamma channel model to basically model turbulence. You can use also log-normal type of models. So gamma-gamma is just a product of two gamma distribution, which means like we assume that there are two scales of turbulence, and both the large scale and small scale are modeled by gamma distributions. And these models are basically parameterized by this particular model by alpha and beta that are given by this expression that are function of the so-called right of variance, which can be written as function of the refractive index, which is the constant if you are having a horizontal path, but if you have basically a slant path or a vertical path from ground to space, you need to integrate over the whole distance, as well as basically the distance between transmitter and receiver. So just to give an idea, this is how, for example, a gamma-gamma turbulence looks like. So obviously, if you have a weak turbulence, the tail will be very light here. If you go toward a strong turbulence, you have a heavy tail here, which means that you have a high probability of having deep fading. Now, why I'm having these two slides, just because later on I will present the benefit of adaptive optics. So one way to mitigate the effect of turbulence is to use adaptive optics. To make a long story short, I mean, the way I understand, I'm not like someone coming from a physics background, but from a signal processing background or communication background, is one way to reverse the channel. So if you feel the channel is introducing a certain transfer function, what adaptive optics allow you to do is basically to reverse the effect of turbulence. So you have like h minus 1 with basically, ideally what you want to get is the original signal. So this kind of compensation can be done basically after fact. We call that post-compensation. So basically this is kind of a typical pure beam. It goes through a turbulence, you get some distortion, you do some compensations after learning what the turbulence was about, and you can correct the beam. Or you can do it upfront, which means you distort the beam, or you pre-distort the beam, knowing the kind of turbulence you'll be facing, and then when it goes through that turbulence, it can be basically kind of come closely to a pure beam type of behavior. So adaptive optics help you basically mitigate or reduce the effect of turbulence. So let me kind of touch a little bit about, and I will go a little bit fast because I know that we have limited time. So some of the effort is about trying to basically minimize the effect of pointing errors. So turbulence is one aspect. The other aspect is pointing. So as I mentioned earlier, pointing basically a receiver and a transmitter at hundreds, if not thousands of kilometers is quite challenging. And ideally what you want to see the beam footprint perfectly aligned with the detector. But in practice, because of vibration we'll see in the X and Y dimension, what you'll capture only is a fraction of the beam. Okay? And that fraction of the beam has been analyzed in a classical paper by Farid and Harovic that was published in JLT in 2007, and basically that gives you how much you can capture given a certain vibration, the X and Y dimension, and the vibration was basically modeled as Gaussian in the X dimension and Gaussian in the Y dimension. Now, we have developed some approach, and I'll skip this part because it's a little bit too technical, and the idea is how we can maybe minimize the effect of pointing, but regardless of that, at the end of the day, you will have to live with a certain level of pointing errors. So going back to the model I just described above, when you look at the type of pointing that you can get, so you have this vibration in the X dimension and the Y dimension. The original model that was proposed in this classic paper by Farid and Harovic assumed that the two Gaussian are basically zero mean with the same variance, which means you assume that you have what we call balanced type of vibration and without bore sight, which means you are by default perfectly aligned, but you have some vibration in the X and Y dimension that are roughly of the same intensity. In practice, you may end up, for example, situations where basically you may have no bore sight, which means in average you are aligned, but basically you have a stronger vibration in one dimension compared to another dimension, which means the Gaussian have different type of variances. Or you may have a bore sight, which means you don't have a zero mean, but you can still have the same variance. So anyway, there are different models that have been proposed. So recently we have, over the summer, established a very nice collaboration with Professor Atta. I see him here, Yalcin Atta from Ankara. And we try to look at the performance of FSO link under basically ground to space configuration, assuming a Hoyt type of basically vibration, which means we assume that we have no bore sight, but we assume a certain generalized model where the vibration in the X and Y dimension are different. And I invite you to go through this interesting paper that are still going through the review process. And here are some of the equations that Professor Yalcin Atta derived. This is the ouch probability under imbalanced vibration, and this is under balanced vibration. As you see, these are kind of expression that they take into account the turbulence as alpha and beta, as well as a pointing error, assuming that basically it's unbalanced. The pointing error are in this kind of expression C here. And if you assume that you have balanced, you can get rid of this integral and you can have a full closed form expression. This is under gamma-gamma type of turbulence, assuming ground to space. And there is another follow-up paper, again with Yalcin. And in this case, we looked at log normal distribution, again under the same kind of, let's say, pointing error, where I assume that you have imbalance between the X and Y dimension. and again we have a nice closed form. Actually here it's an integral, finite integral expression, but if you assume balanced type of vibration, you can get rid of the integral also. So this is just to tell you that there are some interesting basically closed form that can be obtained to characterize the performance of these links and the turbulence under also pointing, accounting for both adaptive optics and no adaptive optic correction, in particular in the first paper. So let's see some of these results, and these are again in this paper with Yalchin that is available on TechRive and that is still going through the review process. So let's try to see what happens. So here's ouch probability as functional altitude. So you have an uplink type of situation, downlink type of situation. So uplink is ground to space. Like here is like a HAPS type of situation, right? So you have ground to space or space to ground, but also of interest is to look at space to space, because you may want to create basically like a cellular network in the air, okay? And actually free space optic can be also a very nice way to interconnect HAPS or satellite, and this has been used also. So what you notice is the most affected type of link is the uplink, and that's understandable. I will tell you why. Then you have the downlink, and then you have the horizontal link. So why is uplink have worse performance than downlink? Because most of the problems are coming from the first 20 kilometers. So basically, if the FSO link get hit right away, as soon as it's transmitted, then basically you have this beam wandering up front, and then essentially you have to kind of live with that kind of distortion until you reach the HAPS. Now the downlink, you have already, maybe you have less intensity and turbulence as you go down. It becomes more intense towards the arrival, and basically the distortion, cumulative distortion is less important. Now when you apply adaptive optics, you get certain gain as expected, because adaptive optics, like when you look at this two-blow curve, this is without adaptive optics, this is with adaptive optics, you say you have a certain gain ouch probability. Now if you look at horizontal links, that's a nice kind of observation, is above 20 kilometers, atmospheric turbulence are basically negligible, which tells you that if you interconnect satellites, which are in the space, or HAPS above 20 kilometers FSO, basically you don't have to deal with atmospheric turbulence problems. Okay, so, and that means you can go through hundreds, if not thousands of kilometers without having much problems. Now, in this context, how can we use this analysis basically to interconnect different layers? So here is like basically our starting point. We are trying to connect an optical gateway station to a satellite. So you can use an FSO link with all the problems we mentioned earlier. So one often approach that is used to kind of make sure that the link remains reliable is to use a backup link, an RF backup link. The RF backup link will be there to maintain connectivity. So obviously, maybe the RF link will not give you the same level of speed that you would like to see with an FSO, but at least it will maintain connectivity. Now, one idea that have been put forward last year in 2021 in this paper, which is another kind of interesting approach to mitigate the effect of turbulence, is to use relaying. Those of you who have been quite active in 4G and 5G, you know cooperative communication and relayed communication has been for many years very popular for terrestrial network. So you use the same kind of concept, but for these kind of aerial and space network. And here the relay is going to be a HAPS. So a HAPS can have a dual function. It can be serving some population from an access perspective, but actually it can also serve as a relay for the backhaul. And the idea is, if you assume, let's say, the uplink, which is where we have most of the problems, essentially that you are having most of the problem by going from the ground to basically 20 kilometers where you have the atmospheric turbulence. So you take that signal, you clean it up, decode it, forward it, and send back to satellite. That's basically the basic idea. Okay? Now, we picked on that idea, and we said, you know what, that's a great idea, but how can we place, or how should we place the hub? What will be the optimal location of the hubs? So intuitively, you may think that the optimal way to place the hubs is midway, right? Like because satellite is not going to be always above you, there will be always zenith angle. So basically midway, you would put the hubs. And actually, although that's the intuitive answer, that's not the optimal solution. The optimal solution after analysis, and it's actually straightforward when you think about it, is always to put the hub exactly on the top of the optical gateway station. And the reason behind that is basically you want to minimize the path over which you are more subject to turbulence. As I mentioned earlier, most of the turbulence is coming from basically the first 20 kilometers. So if you minimize, like when you have like basically a certain zenith angle, this distance can be kind of important. If you try to minimize it, you will basically minimize the effect of turbulence. So that's we have we looked at it from different perspectives. You can look at these two papers that are available on TechRive or Archive, where basically this is a kind of setup under consideration. You have, let's look at an uplink. You have basically a transmitter. You have basically a satellite. You can have the option to go directly with all the problems that can come from turbulence. You have an option to go through a hubs, but that hubs can have different type of locations. And the question, what is the optimal angle? So if you do that particular study, and here is a paper with Yalchin, what is shown here, assuming some log normal type of turbulence, this is the worst kind of scenario. This is if you go for a direct link. Okay? Now, if you start using relaying, you are going to get some gains. Now, and the gains is more important, obviously, when the zenith angle is equal to 0, which means when essentially you put these hubs exactly on the top of your gateway station, because you are minimizing the distance over which your FSO link is going through turbulence. Now, the ultimate solution, obviously, is not only to use FSO, but to use some RF backup link. So we also study this kind of hybrid system, where you have a relayed FSO system backed up by an RF link. What you end up having here, and that's a kind of type of results you can obtain. So, for example, this is in green, your benchmark, kind of a standard hybrid RF FSO system. Like if you add a relay to that, like that's a paper of 2021 I mentioned earlier, you get basically this 4 dB gain. If you go and optimize the location of your, and here we went for an extreme case where the zenith angle is about 60 degrees. So if you optimize the location of the hubs, you can get a 15 dB gain. You back up that with an extra RF link, you get an extra 2 dB gain. So what I'm trying to tell you here, relaying can bring some advantage. Optimally placing the relay can give some huge advantage. Now, the ultimate solution is basically, in order to increase diversity, to have a relayed link backed up by a direct link, because you can create some extra diversity, and backed up by an RF link. Why you are doing that? Because you want to spend most of your time on FSO link. You want to minimize the time you spend on RF link, because as I mentioned to you, RF link come with a lower speed. Okay, to make a long story short, what we showed is by using this particular type of configurations, that obviously this ultimate, we call that the integrated system, allow you, in particular for low zenith angle, to minimize the probability of using RF link, which means most of the time you'll be operating on an FSO link, which means you'll be operating at a high speed, and you will be basically forced, let's say, to move to an RF link only if only in a very rare situation. But if the zenith angle is quite important and you have to leave with a kind of quite far away hubs as a relay, then obviously it will not make much difference. Although you still have some savings, but the probability of having an RF link will be still important. Now, to conclude, and these are the two last slides. One thing we have always to remember with FSO. You can mitigate the effect of pointing by coming up with a very smart and clever path algorithm, positioning, action tracking, and I spend enough time on that. You can mitigate the effect of turbulence through adaptive optics or through relaying type of mechanism. But one thing, really, unfortunately, you cannot do much about is clouds and fog. If they are there, I mean, like with a single station, it's very hard to kind of mitigate that. So the only solution, as I mentioned earlier, is to use site diversity, which means you have a main site and you have not only one but multiple backup sites. So for instance, there has been some papers, this is, by the way, those of you who are interested in this topic, some of the active research is being done, for example, by NICT in Japan, the National Institute of Communication Technology, Tokyo, Japan. They have not only some theoretical study, but also some deployed system with satellite, with FSO. And of course, DLR, the German Aerospace Agency near Munich, where they have also some experimental satellites and some interesting studies. So there are some papers published in this context. When you look at Europe, for example, statistically, you need about 9 optical gateway stations located in strategic places in Europe to make sure that you always have connectivity. If you pick, because where you pick your optical gateway station is very critical. You want to put them in places where the cloud statistics are very favorable, and complementary. And second of all, you don't want to put them in the middle of nowhere. You want to put them where basically there is good internet connectivity, because they have to connect to the internet. So with 9 optical stations in Europe, you have very good, statistically, you have very good coverage. So this is something we started also with our kind of configuration. We assume that the hub's connection is blocked. So we have 2 kind of solutions. Solution number 1, where we have an optical, like a backup site, which is quite expensive. Another solution that can work in the case you have light, basically the kind of presence of cloud, like not very heavy clouds. You, instead of having multiple backup sites, you have just a network of hubs in the air that helps you. That tends to be a lower cost type of solution. And here's my last graph. We show the kind of benefits of having site diversity. So basically, this is your benchmark, a single hop FSO link, a single hop with relaying. Then you have site diversity with a single hop FSO. But now, as soon as you put relaying, you get some advantages. This is the ultimate solution, the most expensive one, 2 sites and 2 relay. Whereas here we have only 1 site with 2 relays, so it's a lower complexity, lower cost solution. Available to us only if you are operating in a favorable cloud type of environment. As you see, it comes relatively close to the ouch probability that is the optimal one by the full solution that requires 2 sites and 2 relays. So with that, I would like to thank you, and I'll be happy to take some questions.
We have 1 question over there and 1 question online, so we can take the one from the audience first. Oh, okay, 2 questions. So you will be next, sir.
Thank you so much, Salim, for a very interesting talk, as always. So you mentioned about the applicability of FSO in terrestrial links. So one of the biggest challenges about line of sight for FSO. So are you doing some stuff in that, how we can cater that effect, that even with a slight non-line of sight, we can make it work? Something in that direction?
Yeah, so, okay, obviously for terrestrial, this is the main problem. Yeah. Because, when you are operating in a terrestrial environment, particularly in an urban environment, you'll be facing kind of obstruction. In air and space, it's less of an issue, right? I hope you agree with me. You are kind of, kind of pointing toward the space. So usually there is no obstacles there. But having said that, as you know, and probably there are some talks on this today, RIS has been a quite active area in the context of creating a non-line of sight of RF. There is also quite a bit of interesting research. For example, Robert Schober, probably you know him in Germany, who have done some interesting work on RIS for FSO. But again, it's mostly for terrestrial application. Okay? For space and air, usually you don't have obstruction because you are pointing toward the sky.
Thank you, Professor, for your presentation. I would like to ask you about the practical solutions for the hub systems. That, as you know, that there are 2 biggest internet companies in the world, and Facebook and also the Google. Facebook started the hubs program in 2014, which is the Aquila, and finished it in 2018. And Google also finished its program, which is Loon, as you mentioned in your presentation, in 2021. I would like to ask you that, by the increasing number of the LEO satellites and the connectivity solutions by the satellite solutions, will the story of the hubs is going to be end, or will be any new projects around the world for the hub solutions?
Excellent question. So, and I think you mentioned 2 interesting facts. Indeed, at least like you probably, the first time I heard about hubs, it was through the Aquila project of Facebook and the Loon project of Google. And both of them, although I think technically they were not a failure, because they were able to demonstrate some capabilities, including FSO transmission with Aquila between basically 2 hubs. However, I think why they failed. I mean, this is just my understanding. Google and Facebook, they are not aerospace engineering companies. They're not even like mobile network operator. For them, the objective is to provide connectivity because they believe, and rightfully so, that connecting more people is going to create more business to them down the road. So they showed the road, they showed the way, basically, that this is a good approach. But if you notice now, most of the hubs development are not done by the Google and by the Facebook. It's done by aerospace engineering companies. This is their bread and butter. These are experts, because these projects fail mostly because they are not able to maintain a long-term flying, a high endurance type of flying condition for these hubs. So if you look now at Thales, you look at Airbus, you look at Stratospheric Platform, these are companies specialized in aerospace engineering. And a hub is not there only for communication. You can think of it as a flying platform that basically, once you put a platform at 20 kilometer altitude with a certain, basically, payload budget, let's say 20 kg, 30 kg, you can put a relay, you can put a radar, you can put a camera for border control, you can put all kind of other, so you can customize your payload depending on your needs. So it can be used for military application, of course, also. So in my view, the technology is going to mature and is going to fly, not only for communication, connectivity purposes, but few other purposes. Okay? And hopefully the technology will be mature, so that basically it's going to be sustainable. Now, is it going to be used for future telecom system? You know, we'll see. But it seems to me that they have a great potential. Okay? And to a certain extent, they may be, to me at least, if I have a huge country like the US, maybe I need a mega constellation. If I have a relatively small country, does it really make sense to invest in a full mega constellation, knowing that most of the time the satellite is not going to be under covering my own territory? Maybe it's better to invest in a few pieces of satellite that can be full coverage, that are under my full control. I have integration, I mean, I own the data, because, you know, when you also send your data through the cloud, you don't know where the data is going. So I think there are some merit to hubs. And as you know, Professor Halim, Professor Gounes was, I know her probably, she was in ITU, now she's in Polytechnic, have been doing some quite interesting research on hubs. So there are a few of us who I think are strong believers in hubs. Now, is it to happen? We'll see.
Thank you very much.
Sorry. Okay, so we have other questions, but unfortunately we're out of time. So Professor Petar is waiting for us, so we will move on to the next keynote. Thank you so much. Professor Petar is the head of section on connectivity at the University of Aalborg and visiting excellence chair at the University of Bremen. His research areas are in the area of wireless communication and communication theory. Throughout his career, he has won numerous grants and awards. He is currently on the editorial board of many prestigious journals, and he has recently authored a book, Wireless Connectivity: An Intuitive and Fundamental Guide, among his many other publications. Welcome, Professor Petar.
Thank you very much for inviting me, and I'm sorry that I cannot be physically present there because of a very tight travel agenda these days. So I guess I can start, right? So why? Sorry? I was just saying yes, you can start. Can you see the slides?
Yes, we can see the slides. We can see the slides, sorry. There's a microphone issue.
Sorry, can you see the slide?
Yes. Can you hear me?
Oh. Okay, excellent. So let me start. I'm going to talk about 6G wireless systems and especially the question of digital time and timing as we are moving towards 6G systems. So this is the outline of my agenda. So I'm going to talk a bit about broader perspective towards 6G. Then I'm going to talk about latency and its friends, like other timing measures. Then I'm going to present a rather general statistical framework for timing, which is encompassing latency, age, and other timing measures. And then I'm going to talk about semantics and goals and the timing constraints, because these days there is a lot of talk about this semantic communication. I think there is no consensus what this actually means, but I think with certain timing constraints, some of the objectives can be well defined. And finally, I'm going to talk about timing in various communication models. So, going towards 6G, 6G is I mean, the whole history started, I think, 3-4 years ago, and there was this flagship center made in Finland related to 6G. So in our community, we somehow, when 5G became mature, we said, okay, what's the next thing, and just we have to call it 6G. So there are many aspects of 6G, what this is going to be, whether it will be a unified standard, how it's going to be affected by open radio access networks and other trends, and so on. One thing which kind of is getting crystallized is that 6G is more than communication. So the 5G triangle, this EMBB, broadband, ultra-reliable low latency, and MTC was about communications. Then it pretty much covers a large spectrum of communication scenarios. Of course, we can tune the performance if we want the higher rate, if we want the even lower latency, but we're going to see whether lower latency is always the answer. And this triangle towards 6G, I think it will be augmented to include 3 other things. One is localization, positioning. The other one is sensing. And all these things, communication, positioning, and sensing, are going to be connected through certain intelligence, artificial intelligence, learning, and decision algorithms. So I think if we're speaking about triangles, so this is the augmented triangle of 5G towards 6G. So this is going to bring interesting problems. For example, in 5G, a big question was that of slicing. So how we are going to guarantee a certain communication service with certain parameters, and then mix up these heterogeneous communication services. Now we have to use the same resources for positioning and sensing, and this is kind of generalizing the concept of slicing. So speaking about Internet of Things, in 5G play a prominent role. There is a very often discussion about 5G and Internet of Things, because 2 out of 3 services in 5G were related to IoT, this massive machine type communication and ultra-reliable low latency communication. So one way conceptually to understand what IoT is IoT is a micro tunnel between the physical and the digital world. So we have a physical world, we are putting sensors are measuring, or the edge can actually try to predict what the sensor would say, take a little bit of data from the sensors, and send the response back. This is different from what we usually see in communication engineering, because in communication engineering, we try to take the message from point A to B as correctly as possible, or with certain distortion measurement. And here, we somehow have an oracle and another device in between, which tries to predict what the right outcome is. And I think this is changing the communication models in very interesting ways. Then another point which I mentioned are the timing references. To understand the timing references, let's take this very simple scenario to see that actually things are getting very complicated even in this simple case. So let's take a sensor which is being monitored by an edge controller, and this sensor is sampling a data, and the data is time t1 is sampled, the value is s1. This data is sent to the edge controller, and it's received at time t2. So the age of the data is t2 minus t1, but the sensor doesn't know this until t3 when the acknowledgement is sent to the sensor, right? So there is a mismatch, timing mismatch between what the sensor and what the edge controller knows. Then look at this TD. TD is a deadline, which means that after hearing the last successful update from the sensor, the edge controller sets a countdown timer, which says that if I do not hear within this time from the sensor, then I'm going to announce that there is a failure, right? So that's why the sensor has to send these regular updates, heartbeat messages. Then the sensor tries to send another message at T4. This message doesn't arrive. Then the sensor tries to send another one at T5. That one arrives. The failure timer is resolved, is reset, but the sensor doesn't know that. And then the sensor again samples the data and tries now very hard to send it, maybe by using higher power or higher bandwidth. And then this is confirmed. So finally, the system is again in a reset situation. So here we have again starting a new countdown timer. And then another operation that would be interesting here is that the edge controller says at time t9 to the sensor, go to sleep after ts seconds, and the sensor acknowledges that it will go to sleep after ts seconds. So that this acknowledgement here is important because otherwise the edge controller would think that the sensor is in failure. So with all these parts of this story, we can actually define three types of timing reference. One is a past timing reference, which is something that happened in the physical world in the past, and then we are measuring the time with respect to that. So we can actually measure the freshness of the measured information with respect to that. Then another one is a deadline. So it's a deadline, it's a future timing reference by which something has to happen. So for example, we have to deliver the packet by this deadline, otherwise the system is in failure. Or we have to deliver packet by certain deadline, otherwise the command actuation cannot take place. And finally, we have a relative timing reference, which is residing entirely within the digital world. It's entirely digital time. So it's a reference with respect to interaction between two digital systems. Here's the edge controller and the sensor. And then how do with taking all these things into account, we can define a general timing requirement. For example, and as we know in statistical operations, there are two basic statistical operations that we can have. One is statistical decision, or more generally statistical classification, and the other one is statistical estimation. So statistical decision means that we are looking into occurrence of some event. For example, let that event be arrival of a packet. Then we can describe it with this curve here, where we look into the probability that the packet arrives by a certain time, given a certain amount of data which is being sent, and the probability that this is going to happen by a certain time, right? And this time can be defined with respect to a past anchor, for example, whatever happened in the physical world, or it can be defined with respect to a future point. Another thing is statistical estimation in time, where we can look, for example, about a quantity which becomes on average more correct over time. That could be, let's say, the empirical risk of a machine learning algorithm. So if you have a distributed machine learning, then the empirical risk over time on average is decreasing because the learning is progressing, right? So so how do we use this to make a meaningful communication in systems? So we can define the semantics and effectiveness when we are in relation to three principal uses of the transmitted data, as I mentioned before. One is joint source channel coding related to reliable storage or exchange of data with a given fidelity. Then in learning on inference, we have a semantics of the data within a given trained model. So how much it contributes to the training of the model and to the decrease of the empirical error. And then finally, effectiveness is inference coupled with actuation. So to do that, we can introduce now, having this the framework, now we can start to introduce various measures of timing. For example, we can say that a value of information is a metric that combines the age and the content of the packet to directly measure what is the usefulness of communication. And this another measure could be urgency of information, which is value of information defined in such a way that the packets with the highest value are the ones that affect the control performance the most. And if age of information was increasing linearly, the value of information actually increases, changes non-linearly, because it follows certain context and certain state of the system that is using this data. To explain this, we can have this. This is from a recent paper on the semantic communication network system, where we are looking into a control of inverted pendulum, and we are seeing what is the value of information that this inverted pendulum is receiving at different times. So the value of information is higher when it's in a critical state to lose stability and so on. So so this is an example of how timing and the content of the data is simultaneously important for the controlled system. Another example of this statistical framework is a timing anchor, where we can have, let's say, a statistical decision for a timing anchor could be push-based updates to ensure freshest update at node 2. So we have a node 1 sending updates to node 2, and then using the statistical framework, we can define timing anchor in the past, and then we say with respect to this anchor, we are measuring how fresh the data is, and then we are trying to deliver this within a time frame which is measured with respect to that anchor. Statistical estimation, in this case, would be the case where the node 1 gradually sends information about its state to the node 2, and then the correctness of this state increases in time. If we have a pull-based system, then node 2 is sending a query to ask node 1 for an update, because the node 2 might have a model, a digital twin, let's say, of node 1, and then is trying to estimate what is happening in node 1, but if it's not certain that the update is correct, it can ask for update. Then another example is this deadline, where we can have, for example, this is the usual URLC thing, where we have a deadline for delivering the packet in the future, and we are trying to see whether the packet is going to arrive with certain reliability. In this case, any semantics or goal or effectiveness of the data is absent, because we just try to deliver packet end to end. So once we start to look into how the packet is used, we can actually change the requirement on the latency and the reliability of the system. And then statistical estimation example is, let's say that the satellite is passing, and then we have a deadline until the satellite becomes unavailable. We have seen examples in the talk by Slim before, where we have various services, and then if the satellites are leaving the horizon, then we have this deadline to deliver something to the satellite by that time, right? And another example is statistical decision could be a consensus. Now there's a big popularity of various distributed ledgers and blockchains, and their collective goal is to achieve consensus. So we are not looking into the latency of a single transmission, but we are looking into the timing performance of the overall consensus. And statistical estimation could be for this relative timing reference, which are purely residing in the digital world, could be a minimization of empirical risk in let's say distributed machine learning. So finally, let's look into timing in various communication models. So if we look at Shannon's communication model, so we always come back to this because it's so general and let's say so useful for making conclusions about communication systems. There is a lot of talk these days about going beyond Shannon model, but to go beyond Shannon model, we first have to understand this model. And the model of Shannon relies on causal relationship among channel uses. So in the model of Shannon, there is no inherently time. So we do not say what is the time between two channel uses of Shannon's model. We define the time in Shannon's model by imposing a structure of sampling. Let's say Nyquist sampling, and then this Nyquist sampling depends on the bandwidth available for the system. Then we say, okay, there are these regularly spaced in time channel uses which are defining what is the timing and what is the duration of a packet transmission in Shannon's model. But as such, Shannon's model is a general mathematical model of causal relationship. There is no time there. So to define time, we have to specify a certain bandwidth and put a certain physical context. And also, it's by design, by our choice, we have decided to space the channel uses equally in time, but we do not need to do that. We can actually do irregular sampling and have these samples in time unevenly spread. Then, having said that, how do we measure latency with Shannon's or timing with Shannon's model? So we have to introduce bandwidth first, and then we have some other assumptions in Shannon's model that there is a instant message decoding, there is no additional latency due to protocol interactions, the sender and receiver are always ready, and data is always available. So once we start to look into when the data is not available and start-stop of transmitting of packet, we are going to networking issues. And this model of Shannon is suitable, for example, to model statistical decision. Let's say there is a lot of papers using finite block length theory with regularly sampled channel uses to see what would be the latency of a short packet transmission, right? And then statistical estimation could be also considered with this model when we consider joint source channel coding, except that the exact timing analysis of joint source channel coding should take into account what is the timing that we need to use for compression. And as I said, this Shannon's model is very general because it's not looking into how the data is used. So there's no inherently presence of semantics or goal in the model. Then, as I mentioned, if we look into the real life systems, then we have compression that takes time and communication that takes time. So if we have a total latency budget in this simple scenario of a single link with the edge control of a robotic hand, then we have a latency budget. And if we have a certain deadline by which we have to spend this budget, then we can spend it on compression to lower the data size, or transmission to make a more reliable transmission. So, for example, if we spend more time on compression, then the amount of data that we need to send is lower, so we can send it at a lower rate, which means more reliably. Or we can use less time for compression, but we can use more time for communication and send the data at a higher rate. So this really depends on what is the compression ratio and the processing capability of the device. If we have a device with infinite computing capabilities, then compression is instantaneous. Then, of course, we spend all the latency budget on communication, but we know that that's not possible. And this is an example of a model we have made for compression and various operations in this link, where we have modeled these compression operations by using a gamma distribution. And then the main point of these graphs is that the more powerful processor you're putting, the better the compression is done, which is kind of obvious solution. And then the easier it is to send the data within a given communication time. Because if the processor for compression is not powerful enough, then we are spending a lot of time for compression, and then there is little time left to do communication, so that little time which is left for communication has to be used with a very high rate. Another interesting measure which we have introduced is this Curiage of Information. And Curiage of Information is to measure how old the information is, not on average, but only in the time when the receiver asked for it. So this is for pool-based communication. So this is the case, for example, when we know that the satellite is sending a regular query request. So this graph is just showing what is a key idea of this. Instead of minimizing on average the query of the age of information, we know when the queries are going to arrive. So we are organizing the transmissions so that the information which is collected at the time of reading has a minimal age, right? So this is an example of a pool-based system with timing anchor. Another step would be, I have like three, four more slides and I'm done. Another thing that we could do is, instead of looking at time, we can look into what is the content of the data. So this is an example where edge node is trying to estimate some statistics of sensor. For example, it could be average value of the sensors, maximum value, or any nonlinear function which is based on the sensor measurement. So every sensor is getting a noisy observation of a certain process where we have update based on the previous state of the sensor plus some noisy update. And then the edge node and the base station there is estimating the state based on the Kalman filter. And of course, it has some uncertainty about the real state. So it tries to get update from the sensors about the state to get as correct as possible state at a given time, at the time of query. And the question is, which sensors should we get update from? So which sensor has the biggest value to compute these summary statistics? And then this summary statistics is, instead of we are looking of the minimization of the square error rate of the sensor readings, we are looking into the minimization of the minimum square error for the function of those statistics, which we are trying to predict. And one thing we have done in this work was the base station is running a simulation, including the packet error. So it says, if I ask this sensor and if there is a packet error, then what will be my state? And if there is no packet error, what will be my state? So it's running Monte Carlo simulation based on sampling not sampling the sensors, but sampling a distribution which emulates the sensor. So it's like a digital twin of the sensors. And then based on this outcome, it decides which sensor should be sampled in order to decide what will be the update to be sent and how to update the value of these statistics. So this graph here is showing that adjusting this the query process to the actual function which is measured is giving the best performance. So this is the error of this new max is the error, and this is the CDF of the error. And for example, in this case, we are measuring the maximum function, and if we do the adaptation of the system to the maximum function, then within the query time we are getting the least error. So this is an example of a system where we have queries which are arriving, so it's pool-based communication, and then we want to deliver it the freshest possible information with respect to the summary statistics, but we do not want to sample all the sensors. So we are just trying to see, like a digital twin, what is the best possible question we can ask in the sensor population. Finally, there is a work on industrial networks where we are not measuring the age within one direction, but we are measuring the age of a loop. So we have a control loop where we have again inverted pendulum which has sensors, is sending over wireless network the data to a controller, and the controller is sending it's sending it to an actuator to tell what the action should be. So we have defined this age of loop also because it's very easy to measure it, because we send the sensor information, we see when the command arrives, so that's the loop time. But it's different from a round trip time because we can decide when to sample the sensor information, right? So that is an element of age there compared to just a round trip time. And what we have shown there is that if you optimize with respect to the loop rather than for the uplink or downlink transmission, the stability is achieved with the actually very small bandwidth. So the point here is that using round trip optimization to optimize a certain timing measure rather than imposing low latency on the uplink and downlink is much better. So this is telling that the latency is definitely not always the best measure to optimize, but it really depends on how we are using the actual data which is transmitted in the system. So with this, I'm coming to my last slide. Is what I tried to show is that latency, age, and similar measures are proxies for certain semantic or effectiveness of the data. And this is generalizing the notion of a pure latency, which has been used in 5G. So I've tried to present a general statistical framework on timing, which is enriched by a number of factors that can determine the context, the timing reference, communication actors, and how the data is used. And we need to look into this actual use of the transmitted data, which could be classified as learning, inference, or storage or exchange, and based on that, determine the timing requirements. And I've tried to provide examples on how semantics and effectiveness are related to timing in different communication models. And with this, I would like to conclude my talk. Thanks.
Hey, Peter, this is Hussein. It's a great talk. Thank you very much. I hope you are doing great. It has been a while. We hope to see you here at some time. Maybe, you know, not this time, but sometime in the future. Peter, we have a very tight schedule, and this is the third talk that we had in the morning, and I think the audience need a break. But what I'm going to do, you know, if those of you, if you have questions, please stick around. And then we have some online people also, they have questions. So let's take a break because really we have tight schedule and we need to keep moving. Please stick around for those who have questions, but the rest you can take the break. Thank you. Peter, you stick around as well, okay?
Yeah, stick around, I stick around.
Alice, online question var mı?